All right, let's just dive right into this explainer. Today, we're looking at the fascinating, honestly high-stakes physics behind how things move, and more importantly, how they stop. We interact with the physics of motion literally every single day, usually without giving it a second thought. But right beneath the surface of your simple morning commute, there's this complex, incredibly precise mathematical reality going on. And today, we're going to completely unpack that reality.
Okay, I want you to picture this scenario. You're cruising down the highway going 90 kilometers per hour. Suddenly, you see an obstacle in the road. How many meters do you think your car is going to travel before your brain even processes the danger and your foot physically moves to hit the brake pedal? It's kind of a terrifying question when you really think about it. But before we can actually solve this mystery and calculate that exact distance, we've got to understand the fundamental laws that dictate motion in our universe.
So, let's start with Section 1, Understanding States of Motion. At its core, in physics, motion just means an object is changing its position relative to its surroundings over time. If your position isn't changing, well, you're at rest. But here's the catch. You have to remember that motion is entirely relative. Think about it. If you're sitting on a high-speed train, you are completely at rest compared to the person snoring in the seat next to you. But to someone standing outside on the platform, you are absolutely flying by. And that beautifully illustrates exactly why direction matters in physics, which brings us to a really crucial difference: distance versus displacement. See, distance is just the actual path length you've traveled. It's what we call a scalar quantity, meaning it only has magnitude, just a number. It can never be zero or negative if you've actually moved. Now, displacement, on the other hand, is the absolute shortest straight line between your starting point and your ending point. It's a vector quantity, meaning it cares about both magnitude and direction. So get this, your displacement can absolutely be zero, even if you've traveled a huge distance, as long as you end up exactly where you started. It's kind of like driving a full exhausting lap around a racetrack. You've gone far, but your displacement is zero. Moving on to our next section, speed, velocity, and acceleration. Now, displacement time graphs are great because they turn these really intimidating motion concepts into super clear visual slopes and curves. With displacement on the vertical axis and time on the horizontal, the shape of the line basically tells you the whole story. A flat horizontal line, that means a completely stationary body. A straight diagonal line sloping upwards shows constant velocity, and that curving line bending upwards, that's the exciting one. That indicates constant acceleration. So the real aha moment here is that just by glancing at the steepness or the curvature of a line, we can instantly understand an object's velocity and acceleration. Because the slope of a displacement time graph actually gives us the average velocity. A flat line means zero slope, which literally means zero velocity, right? A stationary body. A straight, angled line means a constant slope, so the object is cruising along at a constant, uniform velocity. But that curved line, that tells us the slope is changing over time. The velocity is actively increasing. And whenever velocity changes, boom, we have acceleration. And just like velocity, we can map acceleration over time. A flat horizontal line above zero means the acceleration is constant, so the velocity is increasing at a nice, steady rate. If the line angles upward, the acceleration itself is actually increasing. If it angles downward, the acceleration is decreasing. But what about when acceleration completely opposes the direction of motion, causing the object to slow down? Well, we call that deceleration. And that is exactly what happens the moment you slam on your car's brakes. All right, let's jump into the next section, the equations of motion. Okay, I'd like you to meet the three primary equations of uniformly accelerated motion. Now, don't let the letters scare you. U is just initial velocity, V is final, A is acceleration, T is time, and S is displacement. Honestly, try not to think of these as dry, boring formulas you have to memorize for a test. Think of them as literal cheat codes for predicting the future. Seriously, if you know how fast you're going and you know how hard you can hit those brakes, these equations will predict exactly where you're going to end up. Which brings us perfectly to our final section, the physics of stopping. Let's put this into practice. Imagine a driver moving at 20 meters per second. Suddenly, they spot an obstacle exactly 60 meters ahead. Let's say the driver has a reaction time of 1 second, and their brakes provide a deceleration of 5 meters per second squared. The million-dollar question: will the car stop in time? To figure this out, we've got to split the problem right down the middle. We need the distance covered while the driver reacts and the distance covered while the brakes actually slow the car down. Let's break those two phases down. During that 1 second reaction phase, it takes actual physical time for the driver's brain to just say, hey, hit the brakes. During that single second, the car is still moving at a constant speed of 20 meters per second. That means it travels 20 meters before a foot even touches the pedal. Crazy, right? Then comes the mechanical braking phase. If we plug our numbers into that third kinematics equation we just learned, where distance is equal to v squared divided by 2a, we find that slowing the car down mechanically takes exactly 40 meters. So adding those two phases together, we've got 20 meters of reaction distance plus 40 meters of mechanical braking distance. The total distance needed to come to a complete stop is exactly 60 meters, meaning the car will stop just perfectly in time, missing that obstacle by an absolute hair. It is such a dramatic real-world proof of why safe following distances on the highway are absolutely critical. Now, let's circle back to that opening mystery, remember? Driving at 90 kilometers per hour. First things first, we convert that to meters per second, which gives us 25 meters per second. Now, if forensic accident investigators look at a scene and find that a car traveled 18 meters before the skid marks from the brakes even began, well, the math proves your reaction time was exactly 0.72 seconds. We just divide that 18 meters of distance by the constant speed of 25 meters per second. Now, a split second, 0.72 seconds, might sound incredibly fast, but at highway speeds, it eats up a massive amount of road. I think the biggest takeaway from today's explainer is that stopping a car isn't just about having good mechanical brakes. It is heavily, heavily dependent on your own biological reaction time. Physics and biology are completely working in tandem here. Think about it. You could go out and buy a multi-million-dollar hypercar with aerospace-grade ceramic brakes, but your stopping power is fundamentally bottlenecked by the wet wear of your own nervous system. And honestly, that brings us right to the future of transportation. Given that human reaction time has a strict, hard biological limit, we simply cannot process visual data and physically move our limbs any faster than our biology allows. How much faster must future autonomous vehicles react to keep us completely safe? If a computer can step in and effectively just delete the reaction distance phase from our math tables, how dramatically does that change the safety equation on our roads? I'm going to leave you with that provocative thought about the limits of human reflexes and the physics of our automated future. Thanks for exploring the math of motion with me in this explainer today.